Welcome to the next video in the Real Analysis video series, and in this video we are finishing this exercise, and I think we are finishing Chapter 2, Section 1, and so we should be moving on to Chapter 2, Section 2 in the next video. But let's finish up this exercise. So we're stating all the duals for the theorems we just proved for infs, and so here they are. If x is a subset of y, then inf y is less than or equal to inf x, right? So this not only switches from sup to inf, but also switches the direction, like which, is x on the left or on the right. So, by the way, I guess it occurs to me that the proof is so fast for this one, given that we already know this thing about sups and infs, that I might as well go ahead and say, we already know this. And so if you just multiply by -1 throughout, then you get negative sup of x greater than or equal to negative sup y. But you also then can push the negative in and get inf negative x. Sorry, never mind. Sorry. I thought it was that easy, but it's not that easy. So anyway, you would just do a direct proof, very similar to the style of proof that we did in the sup case. So in any case, for 2, the dual is really just switching inf and sup. That really is all there is to the dual. In the inf case, it is very similar, right? You just switch, and I got a typo here. That should be inf. Okay. No, that's not a typo. That's the negative case where things switch. Okay, cool. And then a similar statement for the inf, if and only if, for all epsilon, positive real number epsilon, alpha is a lower bound. And for every real positive epsilon, alpha plus epsilon is not a lower bound. So there's a little bit of subtlety in what you have to change to get the dual, but there they are. Okay, here's the proof of the GLB property, which is the dual of the least upper bound property. And so we're going to say, the statement of the dual is that for every non-empty set bounded below, the least upper bound exists, the inf exists. And so by a very similar proof, we know that negative x is a set non-empty and bounded above, so its sup exists, and then we prove this inequality by merely letting the negative pass into over the inf, flipping it to a sup, and we get I think I'm misstating the logic here. The basic logic is to show that negative x is a non-empty set bounded above, therefore its sup exists, and then from the previous theorem, we know that whenever that is the case, the inf of negative x exists, which is all I'm really using here. So there's the proof. Okay, and so in the next video, we'll start on the next section.